Now we need to talk about the physical properties of stereoisomers and how they compare. A pair of enantiomers are going to have the exact same boiling points, melting points, and solubility. And if you were to take an IR spectrum or an NMR spectrum, they would look identical. The only time that enantiomers exhibit different physical properties is when they are interacting with another chiral substance. In a biological system, for example, we have receptors and enzymes that have their own chirality, and so those receptors or enzymes will interact differently with two different enantiomers. The case here we're looking at is R-carvone versus S-carvone, and you can see that they differ only in the stereochemistry about this carbon. But because of the different orientation in space of the groups on these two chiral centers, S-carvone is going to interact with one receptor, while R-carvone is going to interact with another receptor. And the result of that for us is that S-carvone is going to smell like caraway seed, which I don't know if you've ever smelled that before, but it smells quite different than spearmint. And so because these two different enantiomers interact with two different receptors, that's going to cause a different perception when we smell these. Another type of chiral environment that hopefully you have read about now, either in the text or in the soft chalk module, is plane polarized light. So that's what's done when a polarimeter is used. And so because of the chirality or the handedness of the plane polarized light, R-carvone is going to interact differently with the light than would S-carvone. So it turns out that the S-carvone rotates the light to the right, and the R-carvone rotates the plane polarized light to the left. When a substance rotates plane polarized light to the right, it's indicated with a plus sign. And so S-carvone, if you had a pure solution of this and exposed it to plane polarized light, you would see that the light would be rotated plus 61 degrees. When this light is rotated to the left, it's indicated with a minus symbol. And if we had a pure solution of R-carvone, we would see that the plane polarized light would be rotated minus 61 degrees. Two other terms that you're going to hear used when we're discussing the rotation of plane polarized light are dextrorotatory and levorotatory. Dextrorotatory indicates that the light is being rotated to the right, which is also indicated by a positive sign. And levorotatory means that the light is being rotated to the left, and that's also indicated by a negative sign. Say we made up a solution of exactly half R-carvone and half S-carvone, and then did a polarimetry experiment. What we would see is that the two rotations, so this plus 61 degrees and this minus 61 degrees, would exactly cancel each other out. And so we would have a net rotation of 0 degrees. So this only happens when you have exactly a 50-50 solution. So in cases like this, when you have a one-to-one solution of two different enantiomers, we discussed that the net rotation of light would be 0 degrees. This type of solution, when you have equimolar amounts of two different enantiomers, is called a racemic mixture. And racemic mixtures, we say even though there is a chiral center here and a chiral center here, overall, since it does not rotate light, we say that the solution would be achiral. Another term that you might hear used to describe this would be optically inactive. So any compound or any mixture of compounds that exhibits no net rotation of plane polarized light, we say is an optically inactive mixture or compound. Whenever you have an excess of one component over the other, the net rotation is not going to be 0. So for example here, say that we have a 60-40 mixture of the R to S enantiomers of carvone. We know that the R enantiomer has a levorotatory or minus 61 degrees rotation, and S-carvone has a dextrorotatory or plus 61 degrees rotation. Because the R enantiomer is in a slight excess here, you're going to see that the net rotation is going to be slightly in that direction. And so here we end up with a minus 12 degree net rotation in this particular case. Another case where you have chiral centers, but overall a net achiral compound are mesocompounds. So mesocompounds exhibit no net rotation of light. Another way of saying that is that they are optically inactive, and that's simply because however much this stereocenter that's R is rotating light in one direction, the S stereocenter is exactly equal but in the opposite direction, and so they cancel each other out essentially.